Hello everyone, we are Team Elevate and today we'll be presenting our project for the Office Division for the Solar Decathlon Design Competition. This Toronto Region and Conservation Authority Satellite Visitor Center and Office is located in Vaughan, just north of Toronto at the edge of the city. These maps identify the location of our site as highlighted in red. The local climate of this site is classified as a humid continental climate with warm, humid summers and cold winters with snow. The ASHP standard classifies Vaughan as Climate Zone 6A. The TRCA building is located within the Kortright Centre, surrounded by pristine woodlands, and will be sharing any surplus energy and water with the surrounding buildings to create a sustainable community. The intent of this project presents minimal impact to the site. The form of the building is elevated on pile foundations, creating gentle impact and setting lightly on the land. The goal is to set an example for future developments to follow the principle of modular design.
Our design goals include striving for net zero water, carbon, and energy status in addition to occupant health and well-being, educating the users, and incorporating a circular economy. This sequential diagram showcases the thought process of how the building form was developed. The first stage highlights the screw pile foundations, then the public massing, followed by the offices on top. The top building mass is cladded with vertical wood siding, while the first floor is cladded with a mirror finish that reflects the surrounding site. The intent is to give an illusion of a solid floating mass. The fenestration areas of the building have transparent glass as a material finish, which provides vision openings on the building facades. The benchmark to window-to-wall ratio initially was to follow the 40-60 rule. Meanwhile, our design achieves window openings that are much less. One example includes 28% of window openings on the west facade. Overall, this results in reduced energy loads. The arrangement of spaces within the building are categorized into three core principles that are consistent on all floors of the building. The three categories include service along the north side, circulation through the middle, and main programming along the south. This organization simplifies how one travels within the building in an efficient manner. The typical visitor will enter from the west entrance and be welcomed into the grand four-storied atrium to then be greeted at reception by a tour guide. The tour will start with a look into the service room through the fire-rated glass wall, where mechanical units are made visible to educate about the process. Then, guests can explore the open gallery where informative presentation boards and sculptures are showcased. Next to the open gallery is a conference hall where guest speakers can present to a large audience. From the conference hall, the living machine room is made visible through the interior windows of the shared partition wall. This room provides guests with an understanding of how the building's wastewater is treated and how the plants growing within the tanks are connected to the process of carbon reduction. Just before leaving the building from the east entrance, guests are welcome to purchase refreshments and nutritional snacks from the cafe located under the main staircase. These renders highlight the architectural design qualities that were mentioned in the previous slide. For example, the glass openings in some interior partition walls allow for transparency into the spaces for educational purposes and clear connection from one building program to the other. The second floor of the building consists of private offices that face the south side of the building in order to optimize for solar exposure. The first level of the green wall starts on this floor. Architecturally, the placement of the green wall is aligned with the central staircase in order to provide clear connection when traveling throughout the building. In the perspective of a TRCA employee, they would most likely enter the building from the west, considering if they had parked their car or bicycle in the parking lot. The employees are greeted by the main staircase. As seen in the render, the linear staircase is not only functional, but it also mimics a long rectangular building form itself and accentuates the experience of traveling through the building. The third floor consists of an open concept workstation layout to promote collaboration. The location of workstations on the south side of the building was decided based on optimizing for daylight use. This floor also has a lunchroom, mail supply print room, and dedicated lounge seating areas. As seen in this interior render from the third floor, the open concept workstation area is bright and inviting. Employees have the flexibility to reposition their workstations as best fit to their needs. The fourth floor is very similar to the layout of the third floor, but instead of a mailroom, there is a ping pong room for promoting physical activity. This floor provides an interior render that highlights the open workstation. The visual connection to the other floor levels below, planters used to frame the staircase, and the skylight crowned on top, which provides the most daylight exposure to this level of the building.
This building has a hybrid concrete mass timber structure where the precast concrete panel cores make up the fire stairs, elevator shafts located on the north side while providing lateral support. This remaining structure consists of TCC floors, which take advantage of the concrete's thermal storage properties and are held up by GLT beams and columns with metal connectors to allow for disassembly. The loads are then transferred to the ground through concrete piles. The envelope is broken down into modular panels in order to reduce construction time on site, cost, waste, while improving the quality and providing flexibility for the future reconstruction. To decrease carbon emissions from transportation, the panel sizes were optimized for an efficiency with an average size of 8 meters by 3.5 meters. Using multi-story panels that span between the third and the fourth floor vertically and corner panels, this allows for reduced joints, which improves the airtightness. As the panels hang from the floors of the building, the control layers were designed to be continuous to reduce the effects of thermal bridging. This inverted roof construction with the membrane under the insulation does not interfere with the rainwater collection or the PV array, which improves the hygrothermal performance of the assembly. Modeling through Therm and WFI confirms low impact of thermal bridging and high hygrothermal performance. The panels consist of an interior service cavity for electrical and plumbing services. On the exterior, the panel is filled with dense packed wood fiber insulation, followed by interlocking rigid wood fiber insulation, allowing for easy connection between the panels. They are also connected by a gasket system, which provide a continuous air barrier system. A rain screen with the exterior cladding is also incorporated to improve the facade's durability. High-performance triple-pane wood frame windows are aligned with the thermal plane of the panels and support the interior light shelves and exterior shading integrated photovoltaics. A fiberglass frame triple-pane curtain wall system integrated with vertical PVs are also used on the east and west facades. These control layers are also continuous between the wall panels and the elevated ground floor.
During the preliminary design phase, the base model has been created and simulated with OpenStudio software. Our initial goal was to design a building which relied on natural ventilation without any mechanical systems. However, the simulation data showed that the HVAC is needed. As seen in the tables, in this design, the temperature in some areas of the building would go down to -8 and 5 degrees Celsius during the cold season, while the temperature in the same locations of the building could reach up to 33 and 55 degrees Celsius during the hot season. To utilize the on-site renewable energy and avoid using natural gas, different HVAC systems were tested based on code requirements. The ground source heat pump presented the lowest energy use intensity. However, our team decided on not using this system due to its significant landscape alterations and higher installation costs. The other alternative, which could lead us to net zero building, was dedicated outdoor air systems with fan coil chiller and air source heat pumps. After detailed analysis, it was determined that the chiller required high amount of water for heat rejection, undermining our sustainable water use design goal. Therefore, our proposed HVAC model for the TRCA building is DOAS with ERV, VRF, and air source heat pumps. Combining DOAS with ERV and VRF reduce the building's heating and cooling loads while maintaining high energy efficiency and occupant comfort. With this type of HVAC system, we have reached our target, which confirms our design model would have the lowest environmental impact in terms of greenhouse gas emission. The proposed design also uses heat pump water heater for supplying hot water to bathrooms and kitchens.
As part of our preliminary design, the energy use intensity of a baseline building was determined based on the Commercial Building Energy Consumption Survey and normalized by climate, building size, occupancy, and schedule. The base EUI was simulated to be 107 kBTU per square foot per year annually. The design team envisioned a building that was net zero energy and was able to achieve Toronto's sustainable design requirements for new developments. The Toronto Green Standard, TGS, consists of tiers 1 to 4, and we're striving for tier 4, which is the most stringent. The design target set for the office building was to achieve an EUI of 65 kilowatt hour per meter square, a thermal energy demand intensity, TEDI, of 15 kilowatt hour per meter square, and a greenhouse gas intensity, GHGI, of 4 kilograms of CO2 equivalent per meter square annually. Based on implemented strategies, the proposed design achieves an EUI of 62, a TEDI of 14, and a GHGI of 2.2 annually before renewables, resulting in a reduction of 82% from the baseline. The monthly load profile of the design office building is dominated by cooling loads from May to October and heating loads from November to April. In addition, the electricity consumption graph illustrates that the lighting, equipment, pumps, and water heating are relatively constant throughout the year, while heating and cooling change according to the weather. The pie chart shows the annual energy and use breakdown for the proposed design. Due to the implementation of various passive and active strategies, the energy usage for heating and cooling is substantially reduced, making the internal loads of the office, such as equipment and lighting, the major source of energy consumption.
The on-site renewable energy generation consists of 124 modules mounted on the rooftop. The external shading systems on the south facade, in addition to the vertical static shadings attached to the east and west curtain walls, also have photovoltaic integrated shading devices. These PV shading devices are an important part of the building's renewable energy system and play a role in generating solar energy by transforming solar radiation while reducing cooling energy consumption. The preliminary analysis showed that the available rooftop area would not be able to fulfill the project's net zero goal. Therefore, the parking lot located at the southwest of the building used for implementing 400 additional solar panels to increase the project's capacity in generating electricity. This enabled us to place electric charging stations for building occupants and the visitors using the building's clean energy. As seen in the bar chart, the annual on-site energy production of our proposed building is much higher than the annual energy consumption, which can send the extra energy to the current and future developments of the site. The proposed design allows the office building to not only achieve its net zero energy target, but to also become net positive, meeting our design goal.
Being resilient for a building means being self-sustaining and withstanding extreme weather events. As my colleague has already pointed out, the TRCA building is a net zero energy building. To add to that, it has an integrated system of rainwater harvesting from the roof, wastewater treatment facility using a living machine, low flow fixtures for water consumption, and finally pumps water from the underground well present on site. All of this together generate more water than the annual water demand of the building. Therefore, it's safe to say that the TRCA building is net zero in terms of water also. The site is a possible future floodplain, and so the building was elevated about 15 inches from the ground to counteract that. Finally, the concept of disassembly and reassembly has been taken one step further in the TRCA building by using unique QR codes to tag all materials, in turn setting up a digital tracking system using BEAM in the time of reassembly. The design intent behind the project was to go beyond the scope of reducing energy usage, but to reduce carbon emission also. So life cycle assessment was crucial. In life cycle stages category, stage A, material, has the highest impact of 87%. To counteract that, local manufacturers were used for raw materials to reduce carbon emission through transportation. Moving on, one of the innovations introduced in our building was the usage of mass timber. This gives the structure a vast biogenic carbon storage value, which essentially is sequestering carbon for the building. Other conscious design choices include a no basement design, usage of carbon cure concrete, and organic wood fiber insulation for the low global warming potential. All of this together gives the embodied carbon benchmark for the TRCA building to be 142 kilogram carbon dioxide equivalent per square meter, which is cradle to grave level B. When it came down to circularity, the design team employed a circular model over a linear one, which brought the building's circularity to 78%. Being net zero energy building means zero operational carbon for the building. Therefore, the TRCA building will also be a net zero carbon building in its lifetime. With the COVID-19 pandemic at large now, the importance of healthy air quality has reached an all-time high. TRCA building has operable windows on its facade and skylight, facilitating natural ventilation through the building. Additionally, a green wall with plants like peace lily was strategically placed at the center of the double-skin facade in the west to filter the incoming prevailing winds.
Providing ample daylighting can not only improve occupants' well-being and performance, but it also reduces winter heating loads, electric lighting, and total building energy costs. Light shelves and automated blinds were examined for the south-facing windows to eliminate glare. Additionally, light shelves distribute the light evenly and project light deeper into the spaces. Climate Studio was used to assess SDA and annual sunlight exposure, ASE, of the proposed design. The results show that 55% of the entire building is able to meet the 300 lux levels for at least 50% of the working hours per year. Even though the total SDA was measured at 55% for the entire building, the spaces with the highest occupancy rate, including the offices and conference rooms located on the edge of the building, receive plenty of daylighting year-round. As per the simulation results, no floor experienced high glare and lux levels when light shelves and automated blinds were implemented. Artificial lighting was mostly provided in the path of egress and controlled using motion and daylight sensors. These sensors give feedback to the integrated room control system, which adjusts the artificial lighting. The circadian lighting system within the building uses LEDs to mimic natural sunlight throughout the day. Circadian lights are synchronized with the body's natural circadian rhythm and provide health benefits for the occupants. Light load of the building was reduced by removing any unnecessary luminaire and relying on natural lighting and task lighting. Here you can see the various types of lighting fixtures used in the typical floor plan. AGI 32 was also used to apply the LED illumination to meet lux requirement and lighting power density of ASHP 90.1 standard. The overall system was designed to compensate what natural daylighting cannot provide.
This open office plan provides users with biophilia from the green wall and atrium planters. Users can move around flexible acoustic panels to control noise, shift positions of their sit-stand desks, and control task lighting at their workstations. They can open or close windows and blinds to control temperature, daylighting, and ventilation within their immediate environment. Open circulation spaces, including the central stairs and lounge spaces, promote physical activity and human interaction, improving the health and well-being of the occupants. Throughout this project, the integrated design process was used between all team members in order to achieve the design goals. With all the aspects mentioned previously, our team was inspired by the Living Building Challenge and the WELL standards. We have incorporated strategies from these standards and found that through further development, these standards can be achieved for this project.
The cost estimation of the building was around 10.5 million USD, which is about 251 USD per square feet. This value includes energy efficient strategies, renewables, and biophilic components. A quick market analysis for a generic office building showed the price to be around 200 USD. The difference between the costs is due to the carbon and energy efficient strategies implemented in the TRCA building. However, the building has zero utility costs. A conventional office building using around 300 kilowatts per meter square energy will have a utility cost of around 89,000 USD annually. The building will therefore save its owner around 5 million USD over 60 years, proving there will be a payback of the initial higher construction costs in the long run. Here are some of the projects that inspired us to design the TRCA building. We would like to thank our faculty advisors and consultants for their guidance throughout this design challenge process. As leaders of tomorrow, we hope we made a lasting impression to elevate the standards, bring positive change in the AEC industry, and become an example for future developments. So we thank you from Team Elevate.